Welcome back. In this video, I will go over the experiment for looking at the wicking flow in porous media as well as capillary tubes that are horizontal and inclined. Wicking is the phenomena in which liquid goes into the porous solid under the influence of capillary forces that is affected by surface tensions. This phenomena has a wide range of everyday use. For example, when you clean up spills using a paper towel, you're essentially wicking out the water onto the tissue paper. Let us first consider the simplest example of wicking through a horizontal capillary tube. The ambient pressure we denote as P0, and we also assume that at the base of the capillary, we also have a pressure of P0. The meniscus is formed so that it is concave to the outer vapor phase, so that the Young-Laplace equation requires that there is a pressure difference, a capillary pressure difference, denoted by delta Pc, that is equal to 2 times the surface tension divided by Rm, where Rm is the radius of curvature of the meniscus. If the meniscus is a part of a sphere, then this approximation holds where the Rm equals to R divided by cosine theta, and this is almost always true for very thin capillary tubes. So that we can substitute the Rm in, we can get 2 sigma divided by R divided by cosine theta. The Young-Laplace equation simplifies to 2 sigma cosine theta divided by R. So this is the pressure deficit. So at the convex side of the meniscus, we'll have a pressure of P0 minus the pressure difference required by Young-Laplace equation, which is equal to P0 minus 2 sigma cosine theta divided by R. Because the Young-Laplace condition is not met, so the driving force exists for a pressure gradient that drives the fluid continuously going to the right infinitely until the liquid goes out of the capillary. If we consider the flow as quasi-steady and it is a laminar flow in a cylinder, we can use the Hagen-Poiseuille equation, where the linear velocity is equal to the radius of the capillary squared divided by 8 times the viscosity of the liquid multiplied by the derivative pressure with respect to distance. In this case, we can write it as R squared divided by 8 mu, and the pressure dp dx is just the pressure difference divided by the length x. And such pressure difference is actually the capillary pressure difference. And then if we substitute the capillary pressure difference in, which is 2 sigma cosine theta divided by R, and then we also have x here, then we can simplify this by grouping everything. So we have R at the top cancels out with R at the bottom, and the 2 at the top cancels out with the 8, so it leaves us with 4 mu x, and at the top we have R sigma cosine. This gives us a differential equation because velocity is just the position with respect to time. We also have an x to the right, so we can integrate this differential equation with respect to x, so that we have dx, we write it at right, and we have dt on the left and dx on the right. We need to invert everything here. So we have 4 mu x divided by R sigma cosine theta. If we integrate both sides, we have d equals to 4 mu R theta cosine theta. These are the constants taken out, and then that's just integrating x. And integrating x is 1 over 2 x squared. Simplify this, we have 2 mu cosine theta r sigma. If we write it in terms of x, then we have x squared at the top. If we write it in terms of x, we have x squared equals to p times r theta cosine r sigma cosine theta divided by 2 mu. Take the square root of both sides, and we can write it in terms of r sigma cosine theta divided by 2 mu times t square root. And this is called the Washburn equation. The Washburn equation says that the length, the wicking position, is equal to the constant called the Washburn constant multiplied by the square root of time. So the position is proportional to the square root of time. And where the Washburn constant is just the r theta, r times sigma multiplied by cosine theta divided by 2 mu, where the theta is the contact angle of the liquid and mu is the viscosity, r is the radius of the capillary, and then sigma is the surface tension of the fluid. In the more complicated inclined tube case, we have that the wicking flow that generates a meniscus that gives us the delta PC, which is the pressure difference caused by the capillary flow. However, it also develops a gravitational head that is rho GH that counterbalance such pressure difference. So the total pressure drop is equal to the capillary pressure difference minus the head developed. It will not go infinitely wick to the top of the tube, but it will stop at some equilibrium point where the pressure drop equals to 0. And when that pressure drop equals to 0, we can solve for h, which is the equilibrium rise height. Now let us plug in delta PC, which is 2 sigma cosine theta divided by r, and write rho gh, write the h in terms of x. We have, because here we have a triangle, here is alpha, we have sine of alpha h divided by x, so therefore h equals to sine of alpha multiplied by x. So we have rho gx times sine of alpha. And through this, we can solve for x or h in order to determine the rise height and the wicking distance. For example, if we solve for x, we have that 2 sigma cosine theta divided by r equals to the right side, which is the gravitational head. And if we solve for x, the rho g sine alpha will go to the left. This is exactly the form of the wicking distance. And the h is just x multiplied by sine alpha, so sine alpha cancels out and give us the rise height h. Note that the equilibrium rise height does not depend on the inclined angle. So h is equal to 2 sigma, it depends on the surface tension of the liquid, cosine theta, the contact angle of the liquid, as well as the density rho of the liquid, and the capillary's radius r. However, it does not depend on the alpha, which is the inclined angle. This makes sense because we have another capillary tube of different angle. The head that it develops should be still the same. The head should still be rho GH, and we have meniscus here. And we can derive the wicking equation of an inclined capillary tube using similarly the Hagen-Poiseuille equation by assuming quasi-steady state in a laminar flow in a circular capillary tube, so that the linear velocity equals to r squared divided by 8 mu. dp dx in this case is the full delta p divided by x. And delta p is equal to the capillary pressure difference, 2 sigma cosine theta divided by r, plus the minus the gravitational head, rho gx sine alpha. And the linear velocity by definition is dx dt. So that dx dt equals to r squared 8 mu. The x can be go inside, so that it is rx minus dx being cancelled out. So that we have a differential equation of x with respect to t, and we also have x on the right side. So we can separate this equation and integrate to get the Wicking equation for inclined capillary. This equation is dependent on small x and the big X is the equilibrium Wicking distance equal to the 2 sigma cosine theta divided by rho gr sine alpha that we have seen previously. We can then use Taylor series approximation for the natural log here, and we'll get a term that looks like this. If the ratio of small x divided by big X is small, for example, less than 0.3, meaning that the equilibrium height is big X, but it only proceeds for a little amount, so it is far from equilibrium, then the order of 2⁻³ will cancel because it is negligible. So we have t will be approximately equal to, cancel these out, we have 4 at the top, mu, x cancels out with this x, but there is a square, so x is at the bottom, rho gr squared sine alpha, and then here is a x, small x term at the top. If we substitute the big X in, we have 4 mu x squared rho gr squared sine alpha multiplied by the inverse of big X, which is 2 sigma cosine theta, the inverse rho gr sine alpha. These things cancel out. R cancels out. So we have this also cancel out 2 mu x squared r sigma sine. And if we solve for x, we have x squared equals to, everything goes to the left, so e r theta cosine, r sigma cosine theta divided by 2 mu. Take the square root of both sides, this becomes x. We have now recovered the Washburn equation. For horizontal tubes, horizontal capillary. So we see that if the system is far from its equilibrium, then the Wicking equation for inclined capillary reduces to the Washburn equation for horizontal capillary tube, so that it means that the gravitational effect, the G effect, is negligible. So when this ratio is small, we can have the reduction from the Wicking equation from inclined tube to the Washburn equation of the horizontal tube. I have another video showing the integration steps and the Taylor series approximation steps if you're interested in the mathematical details. And now, using the knowledge of wicking through capillary tubes, whether it's horizontal, vertical, or inclined, can now generalize through wicking flow in porous media. Because in the porous media, essentially it is an array of tubes, cylinders, that the water is wicking through. So we can approximate the wicking flow in porous media also with the Washburn analysis to a somewhat accurate degree, where we have the Washburn equation, the Washburn constant, also have similar form, but in this case we have R of W, and R of W is the wicking equivalent radius, which is the effective cylindrical pore radius that is drawn here. So R here, RW for Washburn analysis. And the wicking equivalent radius is generally 1 order of magnitude smaller than the actual pore radius, because we're doing the assumption that the cylindrical capillary tubes inside the porous media are straight. However, essentially these porous media can be quite tortuous. It has a tortuous path through. So how do we correct that? We correct that by saying that originally we have X, and now we correct for tortuosity using the tortuosity constant, tau, tortuosity. So we have the distance now is tortuosity multiplied by X, where tau is usually greater than 1, so that the distance is traveled longer. So if we correct for tortuosity, we replace the X in the Washburn equation by tau of X, and we compare the form of the Washburn constant for porous media. Essentially, we have that the wicking equivalent radius can be interpreted as the actual radius divided by the tortuosity. And because we have a very small pore radius, the gravitational effect is negligible. So even for a vertical wicking through a porous media, we can neglect gravitational effect. The experimental setup for this lab is quite simple, where we have a capillary tube that is anchored on a ring stand. And then the capillary tube, you can do it with various angle of alpha. You can do it horizontally, vertically, or inclined of your choice. And we'll also have a Teflon cap that is filled with liquid, usually water. And we want the water to have some sort of meniscus, so fill it full but not spilling, so that you can use the lapjack to increase the height. So the capillary tube stays fixed, but you move the lapjack up. And one person would move the lapjack up, and the other person will have a timer. So when the liquid contacts with the capillary and starts wicking, the timer, the person who is in charge of timing, will time at the prescribed interval on the capillary. When is the time that it reaches each increment, so that you can calculate the distance with respect to time. You can do it with various tilt angles, with various capillary distance in various liquids. And for the wicking through a porous media, it is similar, where you have a Teflon cup and then you have some sort of liquid in it. You can have water, for example, and you will also have a strip of filter paper. And again, you move the lapjack up so that the liquid contacts the filter paper, and you have increments where the timer, person in charge of timing, can time the moving through the filter paper. And of course, for the setup, you can tape it onto a ruler. You can do it however you want and have a ring stand here. Ruler. This video, I went over how do we determine the wicking flow through a horizontal capillary as well as an inclined capillary. And the inclined capillary can also be generalized to a vertical capillary. We also look over the wicking flow through porous media, where it's essentially many capillary tubes that has some tortuosity. With the experimental setup, you should be able to complete the lab quite easily, and the heavy lifting would be on the data analysis part.